Hello, ladies and gentlemen. So, for today's presentation, I'm going to present to you about my school project, which is called Microarchitectural Espionage, Design and Evaluation of a RISC-V FPGA Testbed for Microarchitectural Side Channel Vulnerabilities. My name is Emir, and I am a student at Telecom Paris. I'm doing embedded systems, and this has been a school research project that I've developed alongside Maria Mushtaq and also Maharin Khan. So here is a general plan of what I'll be talking about today. Introduction, where I'll give a few background related works as well as motivation behind the work itself. I'll talk about background related work, why we choose RISC-V security. I'll talk about the FPGA testbed architecture, the methodology that I followed, the attack implementations. In this case, I'm going to talk about two attacks, conditional branch prediction attack and also the case study which uses this attack, and also contributions and conclusions at the end. Now, the motivation behind this project is as such. Microarchitectural optimization such as out of order, speculation, and predictors, such as, in our case, more specifically, branch predictors, introduce timing side channels. And these timing side channels can be exploited for malicious attacks known as microarchitectural side channel attacks used to infer secret data. Hence, the goal of this project is to build an FPGA-based testbed to study RISC-V branch predictor leakage and evaluate mitigation techniques. Now, moving on to background and related works. So, why RISC-V security exactly? So, most prior work targets priority x86 or ARM processors, and the Secure and Safe Hardware team, also known as SSH, of my university, Telecom Paris, has prior works on side channel attacks. But they are mainly on Gem5 simulator and RISC-V ASIC boards. And there are also fewer studies focused on open source RISC-V out of order cores, specifically on an FPGA testbed. Hence, this causes lack of reproducible, configurable hardware platforms for evaluation. And it is especially important seen as how RISC-V adoption is actually rapidly increasing in the industry and security critical applications. So, moving on with the presentation, I'll talk about the FPGA testbed architecture. First of all, on the hardware side, I used a Nexus Video, which is a mid-range FPGA, and it was the one that it was the most easily accessible to me, all the while being available on ChipYard. Now, talking about ChipYard, I'll talk specifically about the toolchains that I use. First of all, I use ChipYard specifically for system-on-chip RTL generation, where ChipYard uses Scala, which is a class-based programming language that is used to configure the processor, and it converts it into RTL, specifically Verilog. Sorry. And I also use Vivado to generate the bit stream of the the bit stream of the processor itself. And then for the attack programs themselves, I use bare metal RISC-V toolchain to compile the code written in C into RISC-V bit streams. Now, moving on, for this project, I specifically use the Berkeley out-of-order machine, which is a synthesizable out-of-order RV64GC core with speculation and branch prediction. And since the default boom, which is located in ChipYard, is too large for mid-range FPGA, so my main approach for this project was to systematically scale down the boom core to fit Nexus video, all the while preserving security relevant out of order behavior. Here are the configurations both for the boom core and also for a next line predictor configuration. And this next line predictor is used later on in the FPGA as the more naive predictor. And there will be another predictor called TAG-L predictor, which is a mitigation technique that I will further explain later on. And as you can see, for the scaled boom configuration, I use about 20 to 25% of the components from the default configuration. Whereas the cache itself, I left it be because changes in cache does not affect the test that I will implement. Now, moving on with the methodology. There are 9 key phases in this project itself. Where first I selected the FPGA and RISC-V core, in this case Nexus Video and Boom. I configured the RISC-V core, which is the scaling method that I explained previously, and also I generated the SOC based on the selected parameters using Chipyard. Next, I created the attack codes CBPA and IBVA. I compiled these attacks using the GCC RISC-V toolchain, and then I chose which attack to implement at a given time. Next, I load both the RISC-V bitstream into the FPGA and also the attack code into the processor to test it. I time the measurement using RD cycle, and also I analyze the results to infer the secret data. Now, moving on with attack implementations. Let's first talk about the conditional branch prediction attack, also known as CBPA. So the concept is simple. This attack targets direction predictor state shared between attacker and victim. Partial indexing causes aliasing, where different branches share the same predictor entry. And through a 3-step process, which is train and then victim probing and then probing the timing, this reveals secret dependent behavior. In order to mitigate this attack itself, the idea is to replace the simplified one-level predictor or next line predictor, as I mentioned before, which has strong aliasing, with a TAG-L predictor, short for tagged multi-history tables. And the benefit of using this predictor instead is that it reduces aliasing all the while keeping predictor interference less stable. So here's a snippet of the code. You could say it's the pseudocode of the main attack of CBPA itself, where by using 2 if branches, we can test which branch is the direction predictor goes into. And there are 3 phases behind this attack. The first being the training phase, where the victim calls the gadget with secret control inputs. The second, attacking, where the attacker probes the same gadget with chosen values. And the third, probe and measure, where timing gap reveals the train predictor state. Now, as for the results, here's a snippet of the results comparing the one with the naive next level predictor and one with the TAG-L predictor, which is the mitigation implemented. As you can see, for the original attack, we recovered all 8 bits based on the faster cycle between the value 0 or 1. Whereas for the TAG-L implementation, we only got 8 bits correct, and this is strictly because of luck. It's not because of It's not because of the cycle being different, where we can profit based on this inference, because as you can see, for each bit, the cycle count is the same for the value 0 and 1. Hence, we can conclude that by implementing the tag L predictor instead of a next line predictor, we can surely counteract the conditional branch predictor attack. And a case study which implements the CBPA is a smart clock pin extraction attack, where based on the CBP algorithm, this attack verifies a 4-digit pin with early exit comparisons. Each digit is encoded in 4 bits, so there's a total of 16 secret bits, and the attack recovers bits independently using repeated training plus probing. And the key point behind this practical impact is that it works in minimal embedded style authentication logic. No caches, no speculative loads, no fault injections are included in this attack. So here are the results. As you can see, this is a snippet of the results based on position 0 and 1, where we can infer the leak data based on the value with the fastest cycle or the least cycle counts. This actually demonstrates realistic risk in embedded authentication code. Now, behind this project itself, one of the main motivations, as I explained before, is to make sure that this project is actually reproducible. Because after I'm finished with this project, I would surely want a student or a professor to be able to continue with this project. Hence, I developed a technical user guide which allows students, professors, and anyone actually to replicate this work and also to continue at it to test other attacks. Also, as a side note, I managed to write a paper with my supervisor Mahrin Khan and Maria Mushtaq on this project itself, which was submitted and accepted for this conference, the IEEE International Symposium on Digital Forensics and Security in Boston, MA, which for me is a great milestone, seen as how this project was at first made not to be was made with a limited timeline in mind, but at the end we managed to actually contribute a lot towards the advancements of security in RISC-V processors. And to conclude this presentation, so at the end of the project, I managed to build an FPGA based testbed for branch predictor security analysis on out-of-order RISC-V, specifically using the Boom core, and I implemented both CBPA and IBPA, which is short for indirect branch predictor attack, and a practical smart lock case study based on the CBPA. And I also showed how predictor design choices, aliasing versus using predictor with tags, strongly affect processor exploitability. As such, future works that can be implemented on this project is to implement other known attacks such as Spectre or Meltdown, and also to make this test more available on different FPGA boards. Hence, there is no constraint in terms of materials for other researchers. That is all from me. Thank you.